My name is Joseph Grimes, and I'm here with my research partner, Brendan Chenoweth, representing the Sooner Off-Road team here at the University of Oklahoma, and we are presenting our Spring 2021 Front Differential Research Project. So the purpose of this project was to research, design, manufacture, test, and implement a front differential component in a four-wheel drive system within a mini Baja vehicle for the Sooner Off-Road team here at the University of Oklahoma. We validated our design in comparison to purchasable models as to how well it maximized the durability, safety, and simplicity of the component, as well as how well it minimized the overall weight, cost, and driver input needed by the component. Our design also aims to optimize the packaging and four-wheel drive engagement and performance of the component, while also providing a useful basis for future front differential design within the team. Going forward, it's important to know what a front differential is and how it functions. On the right there, you can see a schematic of a traditional front differential, as you might see in an automobile today. It's powered by a single input shaft, which turns that ring gear, which then splits towards into two axles. And what's important is that those axles spin at different speeds. This is important for maneuverability, as you can see in that picture on the bottom. When a car is going through a turn, its inner and outer wheels travel different circumferences. And in order to travel those different circumferences in the same amount of time, those wheels must spin at different speeds, hence the need for a front differential. So why do we think a custom differential will be better for our team? In the past, our custom built components have proven to be significantly lighter, and so there are some obvious weight benefits. In addition to lightweight components, we also have more control over where we place that weight in the components. Likewise, we have some packaging benefits with a custom built differential. We can choose where we mount that differential and how we mount that differential. And as I mentioned, we have some custom built components already, and so a custom differential would directly integrate with the already custom built reduction gearbox that's in the rear of our vehicle currently. Overall, the custom differential allows for a lot more specificity and selectability in the performance specifications. So previously, the SAE sponsored competition that the Sooner Off-Road team competes in annually required that all vehicles ran a rear-wheel drive powered vehicle. However, in the upcoming competition, the rules mandate that all vehicles run a four-wheel drive, selectable four-wheel drive, or all-wheel drive vehicle. In preparation for this, our senior capstone team from 2019 to 2020 retrofitted parts from an all-terrain vehicle into a prototype chassis of ours that you see in that figure there on the right. This capstone project formed a basis and a starting point for the research laid out in this front differential project. Iteration 1, as you see here, was a direct result of that capstone project. It was abandoned early because of an insufficient power delivery method. Specifically, it utilized a prop shaft, which utilized two sets of bevel gears, 1 to 2 drive shafts, and 2 to 4 universal joints. We had issues packaging this prop shaft, and the selectability of the bevel joints was limited. It also required complex safety analysis to deem the whole system safe.
So moving into what we had determined would be our second iteration and our current design today, we needed to collect some data analysis and some data collection. Specifically, we needed to collect both the front and rear wheel speeds of the car through different types of turns, ranging from very sharp turns to large and sweeping turns. We had determined through using Hall effect sensors, which we had mounted to the front left wheel and the right rear wheel, as you can see in the photograph on the top right, that the overall difference was about 12%. Now, this allowed us to then be able to determine what type of different gear ratio we need to have in our front differential. The second set of data we needed to have, as well as analyze, was the actual experimental output of our vehicle. Specifically, we had done this through, as you can see in the bottom right, using a large torque lever arm mounted to the actual hub of our vehicle, and then actually testing to see how much output we can get through using a spring scale. As a result of this test and the analysis we had conducted, we had noticed it is relatively close to our actual theoretical output and differs by only 5%. Overall, this allowed us to then verify our choice in sprag clutches as they carry a specific torque rating, and it allowed us to make sure nothing will actually break and it will be sufficiently strong. Moving into our actual iteration that we are continuing to work on, we have decided to use a chain drive system to connect both the custom reduction gearbox, which is located on the bottom right picture, as well as the front differential, which is the top right picture. Now, this system uses both a 12 and 15 tooth sprocket to connect these two components, as well as achieve the overall difference in wheel speeds of 20% between the front and rear. And lastly, this overall design allowed us to then be able to maximize the simplicity of the system, as well as minimize the driver input and make the system automatic of when it engages four-wheel drive, and minimize the overall need for someone to actually, participate and make sure the system works. Our second iteration design specifically works through using 4 sprag clutch elements. Each one looks similar to the photograph on the top right, as well as you can see their locations as directed by the arrows into the cross-sectional view below. Each one of these sprag clutch elements is rated for a torque rating of 238 pounds and carries a safety factor for our application of 2.08. Furthermore, in our designs, we have used 6 deep groove ball bearings to ensure that any transverse load is evenly distributed to the actual mounting points of the vehicle. Overall, this design works through transmitting the torque from the center shaft, as you can see located here, to the output shafts of this differential through the sprag clutch elements I previously mentioned. These specifically work through transmitting the torque from a inner race to an outer race through a difference in speeds. So essentially, whenever the inner race is spinning faster than the outer race, torque is then transmitted. So the overall vehicle packaging of our component, you can see here in the bottom left as a close-up of our front differential located in the front of the car. Now, the system, as I mentioned before, connects from the front to the rear using a chain, and it meets all clearance specifications which we have needed for our vehicle, as it does not interfere with any of the engine components or the actual chassis members themselves. In addition to this overall packaging allowed us to minimize the increase in center of gravity by keeping the engine relatively low in the car, as well as the gearbox in the back. And lastly, the overall design of this chain routing system allows for maximum durability, as the bottom side of the chain, which is the side responsible for power transfer, is relatively straight and has minimal bends throughout it. So in our specific design, we also had done a large amount of SOLIDWORKS FEA to optimize and validate all the components which we had found. So specifically, we had determined that all of our components were extremely satisfactory in the actual application of our vehicle, as the fact that they all carried a safety factor of greater than 10. Furthermore, this allowed us to reduce any of the rotational mass of these components and make sure our power transfer method was as efficient and effective as possible. So lastly, our overall design, we had justified through the fact that it is extremely simple and easy for us to manufacture here at the University of Oklahoma, and also that this design is extremely reliable in the fact that if the chain system does fail, it will still function as a two-wheel drive vehicle. And lastly, a big advantage of the system was the fact that we have direct control over the engagement of the four-wheel drive through changing the front and rear sprockets to have a different gear ratio. Overall, the system did have a few downsides, however, particularly as the fact of the reliability and durability of the system is completely dependent on the chain utilized in the system, and the fact that it is extremely sensitive to the chain alignment.
As I mentioned before, this project began where the senior capstone project left off, and so there are some progress updates needed to better inform you as the status of this project. Our gear train is completely designed and all analyses have been performed, and the gear train has been deemed safe, and so we are ready to begin manufacturing on all the shafts and bearing faces needed. Our mounting has also been finalized and we're ready to begin manufacturing for those parts. And overall, the design phase is 100% complete, and we currently have a scheduled design review with senior alumni or team alumni and senior team members. However, this project is ongoing, and so there are a few upcoming milestones we want to mention before we close off. Like I mentioned, there is a design review planned with senior members coming up this week. We also plan to begin your manufacturing of the shafts and bearing faces this week. And then following the successful manufacture of all the components, we will assemble those components to test the fitment of them. And then following the successful fitment, we plan to test and validate the durability and engagement of our sprag clutch design in a controlled scenario. We have been Sooner Off-Road, and thank you.